Okay, let me start chapter 9, Nonlinear Differential Equations and Stability. That is lecture 1. First, stability of linear systems. We have this linear system, this, which is in fact this. And from Calc 3, you know that the y prime over x prime is in fact slope of the line tangent at any point xy. So if x is c, for example, y is b, at point CB, the x prime is speed on x-axis and y prime is speed in the direction of y-axis. So y prime over x prime will be tangent or speed, in fact, or let's say velocity, in fact. The velocity in that direction, when it goes in that direction, that's the trajectory. It's like an object is moving on that trajectory. But anyway, so at point CB, we get this. So this is in fact slope of the line tangent to the trajectory that goes through point CB at CB. And remember, we have infinite, in fact, many trajectories, uncountable trajectories, and one of them goes through point CB. And at that point, the slope of the line tangent is in fact y prime over x prime. It's for every point at that point is this number. Now the question is, what happens when these two are zero? Which means that it stops. So the particle has stopped. So when or where does this happen? Let's look at this equation up here. So the question is, where, at what point does this happen? Okay, let me erase this and look at that. So when x prime is 0 and y prime is 0, this gives me a simple system of equations, in fact. That is this thing, a11x, a12y, 0, and a21x, a22y is 0. So this is in fact this matrix, a11, a12, a21, a22 times xy, and that is 0, 0. Now, I'm assuming that this matrix is not singular, so its determinant is not 0. If this matrix is singular, its determinant is 0, then the second equation is the same as the first equation. So let's assume that they are not the same. Okay, so this gives me just one solution. If that happens, it has just one solution, and that is in fact point x0 and y0, which is the origin. Okay, so at the origin, y prime is 0, x prime is 0, so y prime over x prime is 0 over 0. So which means that it's basically undefined, because that can be just any number. So what does it mean? Well, the trajectory has slope, undefined slope at 0.00. Now we know that the trajectories, in this case at least, they just go towards 0.000. What happens? I can ask this question, do they really reach that point? The answer is no. No, no trajectory ever reaches that point. They get closer and closer and closer and closer, but never reach that point. That's in fact, we will see why this happens and what really that means. So this point at which the slope of the line tangent to a trajectory that never passes through that point, in fact, is undefined, that we call a critical point. So a critical point is where that slope is not defined in a sense. And since the slope is not defined, and if the trajectory reaches that point, then it has some slope, right? Or if that's continuous, then it has some slope. So the trajectory never reaches that point. It goes round and round, maybe it gets closer and closer and closer, and never reaches that point. So that's called a critical point. So for a linear system, critical point is basically a 0.00. And no, I'm just assuming that these two equations are not the same. Assuming that those two equations are not the same, then it will always be 0, 0. So let's start with an example and see what happens. And graphs, I will graph some functions for you here, like the x and y. I will find them and graph them for you, and I will graph the trajectories in the phase plane. That's x, y. That's called the phase plane. So let me. I have discussed this before. So let me erase this thing and start with an example I have prepared for you. Now I call this eigenvalues, both say real and negative. So let's assume that they are distinct. No, but I will tell you what this means. So let's start with this. So it is lambda 1 and lambda 2 are not equal, and they are both 0. They are less than 0, and they are not equal. Okay? So example is this. Well, I have it in the copy, because then I don't want to just give you something on the fly which might not have negative eigenvalues. Minus 3x plus 4y. So x prime is minus 3x plus 4y, and y prime is I have x here minus 3y. Okay, so this is a linear system. A critical point is 0, 0. How do you find it? Just set them 0. Set this 0. How do you find critical points? Set this one and this one 0. 3x plus 4y, 0, x minus 3y, 0. That has only one answer. So critical point is 0, 0. At that point, no slope is defined, and the trajectories never reach that point. Now, well, we know that we have the A, but what's the A matrix? That 3, 4, and 1, negative 3. So determinant of, say, A minus lambda I is in fact minus 3 minus lambda, 4, 1 minus 3 minus lambda. So that is minus 3 minus lambda squared. And minus 4 is 0. This is the lambda plus 3 squared. So that is lambda plus 3 squared equals 4. So lambda plus 3 is plus minus 2. And this gives me 2 lambda. Lambda 1 will be minus 3. Plus 2 is minus 1. Minus 3 minus 2 is minus 5. Okay. So whenever you have this, whenever these two are the same, then you will get something like this. That's lambda plus or minus something squared. Don't expand this thing, because you can solve like this easily. Don't, because if you expand, you will get the same answer. But you expand, then you have to use the quadratic equation, quadratic formula. But this is easy. So whenever these two are the same, just do this. Okay, now I have found that eigenvectors, there's no point in trying to find them. So V1 will be, this gives me the two eigenvectors. V1 I found to be, what's that, 2, 1, say, and the V2 I found V2 minus 2, 1. Okay, so the solution, general solution will be this xy c1 2 1 e to power minus t plus c2 minus 2 1 e to power minus 5t. Now I have to give you. I should start at some point in the phase plane. So let's. I have assumed that it starts at point. Let me check my notes. It starts at point minus 2, 5. So let's assume that it starts at point minus 2, 5. So let's say x at 0 is minus 2 and y at 0 is 5. So it starts at this point in the phase plane. And using, okay, so what is this? This is in fact minus 2 is, this is at 0, so it is 2c1 minus 2c2. And this one is 5 equals c1 plus c2, right? So I have c1 minus c2 is negative 1 and c1 plus c2 is 5. So if I add them, I have 2c1 is 4, so c1 is 2. If I subtract, I will get 2c2 is 6, c2 is 3. So the solution is this. X is c1 is 2, so it is 4 e to the power minus t, and the c2 is 3 minus 6 e to the power minus 5t. And the y will be c1 2 e to the power minus t, c2 plus 3 e to the power minus 5t. Okay, so I have said that and I say it again, so this is like parametric equations for a particle that is moving in a plane, and it starts at this point. So at time 0, it is at this point, 0 and minus 2 and 5. So it starts here, minus 2, say it's minus 2, and 5 will be somewhere here, right? I told you that's minus 1. So 5 will be somewhere here. So it's somewhere like here. Okay. So at point minus 2 and 5 is this point, say, and it starts as time passes. So this is time equal to 0. And if you graph this thing, if you parametrically plot this two, or just plot the, if you parametrically plot this on, say, mathematical, for example, parametric plot. If you parametrically plot them, xt and yt, and let me just write xt and yt, for t from 0 to, say, something, 5, something, I don't know. T from 0 to 5, say, then it will give you something like this. Right? Now I have graphed it. So, I'm not sure, does it go, no, so it goes like this. Yeah, it doesn't go below this thing, so it goes like this. Goes towards 0.00. Okay? So, starts here and gets closer and closer. It's interesting if you graph it for any time, just let the time be, say, 5 million. It never reaches that 0, 0. It gets closer and closer and closer and closer. Just imagine. Now, one thing is, why does it go this way? But let's look at this more carefully. Let me plot each one separately, so you can see what they look like separately. And I have the two plots here. So the it starts at 5 and goes like this. The other one starts at the -2 and goes like this. So this guy here up here is x. So so this up here is the x of t, this guy, and this one here is y t, xt y t, these two. And you can see that because I assume that it starts at -2, so you see it starts at -2, that's the x. And this one starts at 5, it starts at 5. Okay, and this is time. This is time, and this is the axis for both x and y. It's not x or y axis, it is just the axis for these two. Okay, so I have found some points like to tell you what, for example, at certain time, say certain time. So at time equals 1, for example, it's almost say, so at time equals 1, I calculated this, it's about 0.2 and 0.9. So it is like, on this one it is like 2, is it 2? No. So let's say it's 2 here, and it's 0.9 here, right? And what are these two on this picture? Gee, it can't be 0.9, but anyway, so this should be lower, right? That's going to be 0.9, just low. So it goes like this. Okay. So for example, this one is 2, say. So that's the x, and the y is 0.9, say. So this y is also 0.9. Okay, so the 0.9 and 2, and this is in fact this point, right? These 2 points give me this point. These 2 points, the x and the y, give me x, y here. You see, this is the x and this is the y. This x, that's y. So and these are x and y separately. Those two are x and y separately. And if I just take them for every time, this is time. So time is implicit here. You don't see time in this picture. Time is implicit. Both x and y are functions of time. That's what parametric means. So time is implicit in this picture. In the trajectory, you don't see time. But you just see that it is moving. So at say point, you say 1 second, say it is like here. At point 0, it is 0, 1 second, 1 minute, whatever that is, it is here. And on this one, you can see that the x is 2 and the y is say 0.9. I didn't calculate that exactly. You can calculate and find. I'm not sure if for 1 you should put 1 here and find x and y. It's somewhere, okay? So the trajectory is related to these two separately. And you can see that this goes to 0, this one also goes to 0. Why do they go to 0? Why? When time gets larger and larger, they go to 0. Look at these two. Look at x and y separately. X itself, if you look at x separately, that is a linear combination of what? Linear combination of e to power minus t and e to power minus 5t. Y is the same, some linear combination. So each one of them is a linear combination of those two functions, e to power minus t and e to power minus 5t. What do they look like? E to power minus t and e to power minus 5t as t gets larger. That's minus t. So both of them go to 0, right? Each one of them is like this. They start at when t is 0, that's 1, they start at 1. E to the power minus 5t goes to 0 so fast, the other one slowly. So they both approach the x-axis. When they approach the x-axis, it means they are going to 0. Because that x-axis, so it shows us this is the value. So the value gets smaller and smaller and smaller, which means they are getting closer to the x-axis. Anyway, so a linear combination of those two, which become 0 in infinity, as not exactly 0, they approach 0. They are two very, very small numbers. Very small numbers. And the linear combination is just some constants times these two. So those constants really don't matter at infinity. At infinity, both of them are basically 0. So this might be 0.000 blah, 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 something, the other one 0.000 blah, blah, times 6 and times minus 6 and 4, that will give you basically close to 0, not exactly 0. So, and you can see here, you can see that both of them are approaching the x-axis. So the values are approaching 0. Now what happens here? Here, as they approach 0, this x approaches 0, this y also approaches 0, right? So as time goes to infinity, x goes this way and y goes this way, y goes this way, x goes this way, y goes this way, right? X this way, y this way. So here they're approaching the t-axis. Here, when you graph them together or put them together, this is approaching 0.00. The trajectory is approaching 0.00. Okay, so what do we say? I'm just by looking at this thing, if that is the response of some system, so it's like, I'm not saying it's vibration, it might be, but there's some system that it starts at time 0, and the system, whatever the response is, whatever that is, it goes up, goes to 0, this one starts here and goes to 0. So both systems, both x and y, which are something related to a system, some values related to the system, some quantities of the system, like for, if this system is a particle that is moving, for example, those are the x and y coordinates of the particle. So those two are going to 0. And here in this picture, the phase plane, the trajectory is approaching 0.00, going towards the origin. We say that this is stable. As you can see, in the long run, physically speaking, the system stops. But mathematically speaking, it never stops. But physically speaking, it stops, right? So in the long run, you can say just it's like vibrating very slowly. Okay, so in the long run, it basically kind of stops. So that is stable. Now, why is it stable? As I mentioned again, and I mentioned it again, it's because of these two. Because of those two, e to the power minus t, e to the power minus 5t, they both become small and small, small and small. So any linear combination of those two, which any solution is a linear combination of those two, right? So that goes to 0. Any solution goes to 0. Any solution, which means if you start at any point, it should go to 0. Okay? Any point. So if you start, say, here, it should go to 0. And in fact, the phase plane, if you graph the trajectories in phase plane on Wolfram Alpha, for example, or mathematical, if you have it, you will see that they are like this. They don't intersect. In fact, they never intersect, but they get closer and closer to 0 this way. This way. Okay, so all the trajectories go towards 0. Wherever they start, wherever they are at time 0, they might be way up there in the universe, somewhere in the universe. Eventually, if that 0, 0 is like the Earth, for example, they get closer and closer to the Earth. Okay, so so that is story when, no, well, I didn't finish the story. So these two are related to this minus t and minus 5t, right? So where did they come from? That is minus 1t and minus 5t. Those were the eigenvalues of that system, right? Because the eigenvalues were negative, this happened. So two negative eigenvalues give me stable solutions. All of them are stable. Because all of them have that e to the power minus t and e to the power minus 5t. So we can conclude if we have, so because in general, if the two eigenvalues are negative, yeah, I have it in here, I didn't erase that. So if the eigenvalues are negative, y1 is not equal to y2 and both are negative, then I have e to the power lambda 1t and e to the power lambda 2t, and solutions are linear combinations of these two, right? Linear combinations of these two. And I know that if they are negative, both of them are like this. They both go to 0 as t goes to infinity. Lambda 2t also goes to 0 as t goes to infinity. So any linear combination also goes to 0 as t goes to infinity. So we call this situation, because they all getting close to 0.00, we call this thing a stable node. So a stable node is when lambda 1 and lambda 2 are distinct and less than 0. Okay? So that 0.00 is called node, and lambda 1 and lambda 2 are distinct and less than 0. So this is the situation that we have stability. Now, what happens if they are positive both? Well, you can guess. Positive means what? They go the other way. They're divergent. Well, let me write another example for you. Let's example 2. Let me erase everything here. And in fact, this should be written asymptotically. Stable. And you know why? Asymptote means that the x-axis or the t-axis is the asymptote. It's horizontal asymptote. And the point 0, 0, 0 is like they approach that asymptotically. They are approaching this asymptotically stable node. So that's the only situation when the eigenvalues are both negative and distinct. Okay, so example 2, again, I wrote an example which, in fact, that's the opposite of this. Not the opposite, but very similar to this. If I write 3 instead of minus 3, that is y. So example 2, eigenvalues both real and positive. And also distinct. So I have x prime is 3x plus 4y. Y prime is x plus 3y. So the A matrix, coefficient matrix is 3, 4, 1, 3. Again, you see these two are equal, so this one is easy to solve. We don't need the quadratic formula. So determinant of A minus lambda I is 3 minus lambda, 4, 1, 3 minus lambda. So I have 3 minus lambda squared minus 4 again equal to 0. I can write this lambda minus 3, no difference. Right? Just multiply by negative 1 inside and nothing happens. Equals 4. So lambda minus 3 is plus minus 2. So lambda is 3 minus 2 is 1, and 3 plus 2 is 5. Well, you can see that I got the two answers with the opposite one. So 1 and 5, and V1 gives that gives me V1. I calculated V1. I guess I got the opposite of those two. V1 is minus 2, 1, and the V2 is 2, 1. So the two solutions will be like this. Let me erase everything, and the two solutions will be x and y. C1 minus 2, 1 e to the power t plus C2 and 2, 1 e to the power 5t. Now I start this one at point, what point? Minus 2 and minus 3. So let's start at minus 2, minus 3. So let's say x at 0 is minus 2 and y at 0 is minus 3. So just do the same thing, and I found x to be, x is 2 e to the power t minus 4 e to the power 5t. And y is minus e to the power t minus 2 e to the power 5t. Okay. Now, it's interesting if you graph this thing in phase plane, parametrically plot these two times starting at 0, then it will be something like, so it starts at -2, -3, so if this is -2, say -3, it starts somewhere here, right? And then it just escapes, goes this way. And you can see why it goes this way, because this e to the power minus 5t as t gets larger and larger, this is larger than this. And both are negative. This is minus 4 times this, is minus 2 times this. So these two dominate this. E to the power 5t, when t is say 5, 10 for example, that's e to the power 50, this is e to the power 10. This is way bigger than this. So this is too negative. It just eats this one, say, just dominates the other one. So that's why you see that it goes to infinity this way, both negative. And well, you can guess that this, well, it starts at time 0, but if you assume that there is negative time, you can see that it gets closer to 0 in negative time, say, this way. But never reaches 0, in fact. If you graph it for negative time, it never reaches 0 again, 0, 0. And for the same reason. And also the critical point is the same, 0, 0. For linear systems, when this matrix is not singular, or the determinant is not 0, we will have what? x0, y0. That's the only answer. So for linear systems, that's the only critical point, and no trajectory reaches that 0, 0. Now, let's graph these two separately. So that was like parametric plot. The x and the y was the parametric plot. Parametric plot of this gave me that, and the parametric plot starts here. And if I plot them separately, they're just functions of time. Just functions of time, and they look like this. In fact, I plotted them. In fact, both are negative. So no, this one x starts at -2. So let me put 0 here. This one starts at -2. This one starts at -3. And I had this picture here. No, -2 was like this, and -3 was like that. So the -3 goes like this. The -3 goes like this. Okay. And in fact, I found exactly this time I found the exact for time. This is time, and this is the x and the y. Which one is the x? This one below this the y. In fact, this one is the y, and this one is the x. And for point 2, in fact, I found that for point 2 I found minus 665 minus 8.4. So for point 2 I found this and this. So this is point minus 6.65, and this is minus 8.4. So this is the x, and this is the y. So x is 6.65, and y is minus 8.4 minus 6.65, and that's this point here. So this point, this is time 0, this is time equals 0.2. So at time equals 0.2, it is at this point. And you can see that it just goes to negative infinity. Negative infinity, this also goes to negative infinity, right? Both x and y go to negative infinity, and separately you can see that they are just diverging. So this situation is in fact when it's divergent. And we say that this is unstable node. Unstable node. So let me summarize here for these two examples. Well, if I didn't give you the phase xy, if I just graph some streamlines, the streamlines should, they look like this. So the streamlines will be like this. Let's go this way, then go this way, and if you start here, it goes like this, and it goes like this, and here it goes like this. So you can graph this thing on mathematical or not from alpha, and if you don't remember how to graph it, that's stream plot, and give the, what was that, 3x plus 4y, comma, x plus 3y, and you can give x goes from, I don't know, minus 5 to 5, and y goes from minus 5 to 5. It doesn't have to be the same, but you can do something like this on mathematical, and you get this stream plot. And one of them was our solution, the one that starts at -2 and -3. Okay, and you can see that they are just going to infinity. Wherever they start, they go to infinity, but it depends on where they start. They might go like this to infinity, like that to infinity, like this to infinity, and so on. Okay, now, the other situation, well, I have to summarize. So, lambda 1 and lambda 2 distinct, now, both negative, we have asymptotically stable node, both positive, unstable. So if they are both positive, as you saw, the two solutions, whatever they are, they just go to positive or negative infinity, it depends on the situation, and that is not acceptable, at least if that is a system, it will break. Boom. So these are the two situations that we have distinct and not the same. Okay. Well, let me find one that has two eigenvalues. Well, I will explain then because I don't want to just. So what happens if they are distinct? Well, if they have a different sign, then they should be distinct, right? So y1 and y2 have different signs. What happens if they have different sign? So let's say lambda 1 is bigger than 0 and lambda 2 is less than 0. So solutions are linear combinations of these two, right? Solutions are linear combinations of e to power lambda 1t and e to power lambda 2t. And yt also another linear combination of these two. Well, depending on the linear combination, depending on the positive, negative, whatever that is, this is what happens. When this is the less than 0, so it is e to power minus 5t. So this goes to 0 basically, right? As time goes to infinity, this one goes to 0. What happens to the other one? This one goes to infinity, right? So I have something that goes to infinity depending on the coefficient of that linear combination. It might be negative infinity, or it might be positive infinity. But the other one is what? The other one is basically, if t gets larger and larger, that one goes to 0. So this one basically is talking, say. And unless the coefficient of this one is 0. Okay? So what happens here is that as time goes, when time gets larger and larger, depending on the situation, we might have stable or we might have unstable. So this situation depends on where you start or what coefficients you have, things like that. So I will give you a much nicer example in the next lecture and graph everything. But this one is like what we call a semi-stable situation. So I will write down an example for you. I don't want to just jump on some example on the fly, and then I don't know if the two are of different signs. So I should look up something for you. Okay, so that was lecture number 1 on the two situations of stability, and the first one, both negative, is desirable. So if you are designing some system, you have to be careful to design it so that the eigenvalues are negative, for example. Now, the situation that we have, say, complex eigenvalues, that's another situation, and I will discuss it in the other lectures that come after this. Okay, so see you next time.